Okay, so now we're going to talk about chemical equilibria, and we're going to start with some definitions of terms, and we are going to then use these terms over and over and over and over again. So it's the kind of thing that if you get good at it, you're going to realize we're using the same tool to do a lot of different things, and it's going to be easy. If you don't quite get it, then it may be difficulty upon difficulty. So let's look for some simple here. So first of all, we're going to talk about where we've been, right? So in the past, we've been here. Let me get my marker ready. In the past, we have said, all right, so if you've got this, say, dinitrogen tetroxide, it might go, and we've said this, produces, right, 2 nitrogen dioxide, right? But we're now going to appreciate that all chemical reactions, to one degree or another, are actually reversible. Okay? To one degree or another, all reactions are reversible. So can you see how this bottom one here is the opposite of the top one? If this is reaction 1, reaction 2 is the exact opposite, right? And that's because chemical reactions are, to some degree, reversible. Now, reactions that have an appreciable reverse reaction, that is, if it's non-negligible, like it's not 1 times 10 to the negative 47, right? If reactions have an appreciable reverse reaction, then we sometimes say, let's talk about both these reactions together. And we're going to call this chemical equilibria. And so in this particular instance, what we're saying here is that dinitrogen tetroxide produces nitrogen dioxide, and nitrogen dioxide produces, right, that's what this is, produces dinitrogen tetroxide, all right? And the way we would read this, we would say dinitrogen tetroxide is in equilibrium with nitrogen dioxide, right? And that's how we say that this is in equilibrium with, and that is if both of the reactions, forward and reverse, go to appreciable extents, okay? So let's look at this now. When dinitrogen tetroxide is placed in a closed container at 100 degrees Celsius, a reddish-brown color develops due to the formation of NO2 because NO2 is brown, all right? So when we put dinitrogen tetroxide in a closed container, we do see some brown forming, right? The forward reaction does occur. Now, as NO2 builds up, it can react to form dinitrogen tetroxide, and the reverse reaction occurs. At equilibrium, the amount of reactants and products stops changing. The actual amount stops changing at equilibrium. That is, if we have A is in equilibrium with B, at equilibrium, the amount of A doesn't change anymore. We would say, it's constant, right? The amount is constant. So let's look at this as a graph. So over time, let's suppose we've got a bunch of dinitrogen tetroxide. So it starts up here, 0 nitrogen dioxide, right, at time 0. And there's no, you see how the red curve here represents the amount of NO2, right? So we have no NO2 at the beginning. And everything we have is N2O4, right? So as time goes on, the N2O4 drops and the NO2 is being formed, right? So as it's being formed, then, right, this is being consumed. This is being produced. And over time, eventually, once it gets to this point here, then there's enough NO2 that they actually start bumping in together and making N2O4 again, right? And so at equilibrium, this is where equilibrium is right here. At equilibrium, the amounts stay constant because both the reactions, forward and reverse, are going at the same rate. Okay? So the rate of the forward reaction starts out fast, but I'm just repeating what I said in the previous slide. The rate of the forward reaction starts out fast, but it slows down as the concentration of N2O4 decreases. The rate of the forward reaction starts out fast, but it slows down when we get less of that. Okay? The rate of the reverse reaction starts out slow. The rate of the beginning reaction starts out at 0, right? But it speeds up as the concentration of NO2 increases. Once the rates of both reactions are equal, we say that equilibrium is established. No further changes in the concentration of either gas occurs unless the temperature or the volume of the container is changed. All right, so this is how we might say that in a graph. The reverse reaction starts out at 0 because there is no NO2 at the beginning, right? So you're not going to have any of the reverse reaction if you don't have any of it. But once we start getting more NO2, then the rate of the reverse reaction starts going up, right? And it turns out the rate of the forward reaction starts going down. And then when the rates are equal to each other, we say we are at equilibrium, okay? Lost my place here. Go back here. All right. The amount of reactants and products are ordinarily not equal to each other at equilibrium. That's one misconception that that's easy to fall into. And as you might think that the amounts are equal at equilibrium, but that's not true. It's the rates that are equal at equilibrium. Although the amount of reactants and products remains constant, the system is not static at equilibrium. This is misspelled, sorry. Chemical equilibrium is a dynamic process. Even though the amounts are constant, the reactions are still going. So we're getting some of that and getting some of this. So equilibrium doesn't mean that these reactions are stopped. It means that the amounts are constant and that the forward rate is equal to the backward rate. And that is an introduction to the terminology that we need for equilibrium.